Hello everyone, this is Professor Keen. We have been talking about Galileo's dialogues concerning two new sciences. And where we left off in the last lecture is Galileo talking about the relationship between music, or more specifically music theory, and pendular motion. And in the context of that discussion, we came across a relationship between the frequency of vibration of a guitar string, for example, and various quantities like the tension in the guitar string and the mass per unit length of the guitar string and the length itself of the guitar string. And I guess so that's where we came from. Where we're going next is into chapter 6, where Galileo is going to step back from this and begin talking about the strength of materials once again, specifically how hard it is to break beams. Okay, so we're in a transition right now in between two topics, and so I'd like to take this opportunity to kind of finish up our previous discussion on natural frequency and vibrations, and specifically to talk about the relationship between natural frequency of vibration and dimensional analysis. This is a very important topic that's used very often in physics, and so I'd like to spend a few minutes discussing this. It's not something that Galileo talks about directly in his dialogues, but the idea is that the vibrational frequency of many physical systems can be determined by looking at and doing a dimensional analysis, that is, analyzing the dimensions of the quantities that affect that vibrational frequency. So it consists of basically identifying the kinds of physical quantities that are likely to affect the vibrational frequency of a naturally oscillating system, like a pendulum or a guitar string, for example, determining the dimensions of those quantities, and then finding a suitable combination of those quantities that gives the correct dimension of frequency or vibrational frequency. So what I should probably do is give a brief overview of dimensional analysis. And so what I'm going to do is I'm going to cut away from my webcam and show my sketchbook. Okay, so what is meant, here's the question we're asking. I'd prefer to use gray. So what is meant by the dimension of a physical quantity? Meant by the dimension of a physical quantity what is meant by the dimension of a physical quantity, and how can dimensional analysis help us. Oops, my sketchbook is freezing up a little bit here. Let's wait a moment. How can the dimensional analysis help us to identify the vibrational frequency of an oscillating system? So let's take the first of these questions first. What is meant by the dimension of a physical quantity? So I'm going to make a table here. This is going to be a fairly large table. And this is a table on units and dimensions. So let's identify certain quantities. So I'll put quantity in this column. And I will write down a symbol that we typically use to represent that quantity right here. And let's identify the units that we use for this quantity. And we'll focus for the moment on the MKS system of units, the meters, kilograms, and seconds system of units. Of course, this is part of the international system of units that was developed in the early 1800s, late 1700s, early 1800s by Napoleon, under Napoleon. We'll also mention some other kinds of units, other units that this quantity is sometimes measured in. And then we'll identify more generally the dimension of this quantity. Okay, so let's start with this pretty straightforward one when we want to know the length of something. So we've got a table, we want to know how long it is, the length. We often identify this in physics formulas by the symbol L for the length. And what are the MKS units of length? Well, you're probably used to this, it's the meter. If you wanted to use a CGS system of units, you might use the centimeter. You could also use the inch. If you wanted to use the imperial system of units, there are all different kinds of units one could use. One could use a furlong or some other more esoteric system of units, or the cubit. We've been using cubits a lot. That's one of the systems that Galileo used. And by the dimension of this, we'll just call the dimension L also. I know this is the same letter here, and I hope this doesn't confuse you, but the dimension is the dimension of length. Okay? It'll be clear where I'm going with this in a few minutes. Another quantity that comes up that's important is mass. And the symbol that's used for this is sometimes a capital M or a little m. Okay? And what kind of units do we use for this? Well, in the MKS system, it's kilograms. Another system we could use is the gram. I guess that's still the international system, but CGS instead of MKS. Other units of mass, sometimes Newton talks about grains, a grain of mass. There are other more, again, esoteric system of units that we could use. All right, and the dimension of this would be just mass. That's the dimension of mass. Okay, what about time? That appears in many physical systems. The symbol for this is going to be either the capital T for time or a little t for time. The units we use are often seconds. You could use other kinds of units if you'd like. You could use pulses or heartbeats for measure of time. You could use something, so heartbeats. You could use days. You could use fortnights. You could use all kinds of different things. How many fortnights are there? Okay. And this has the dimension of time. Okay, time has a different dimension than mass, has a different dimension than length. Okay, what about velocity? Here's another quantity that shows up. This is a little bit different because it is a composite quantity, so it's sometimes denoted by a capital V or a little v. The units in MKS are meters per second. Meters per second. We could also use feet per second, or inches per second if we wanted to. And the dimensions of this, well, since it has dimensions of how far you go in a given time, it has dimensions of length over time. So it's not a fundamental dimension, it's a combined dimension, length per time. So anytime that a velocity appears in a formula, the dimension of that quantity is going to be length over time. Okay, here's another one, density. What do we mean by density? How much mass there is per unit volume. The symbol that's often used is the Greek letter rho. We've come across that before in this class. In MKS, it'd be kilograms per cubic meter. We could also use grams per cubic centimeter if we wanted to. That's also International System of Units, but using CGS. Okay, and what are the dimensions of this? Well, it's grams in the numerator and cubic centimeters in the denominator, or kilograms and cubic meters. So it has a unit of mass per length cubed, right? Because that's a volume, and here is a mass. So it's mass over volume, and mass has units of dimensions of m, and volume has dimensions of length cubed. Okay, I think you're maybe getting the hang of this. Let's talk about frequency. Frequency, denoted often by the Greek letter, the letter F, sometimes by the Greek letter nu. That's another way. Don't confuse that with a V for velocity. That's a Greek letter nu that's used for frequency sometimes. What are the units of this in MKS? Well, it would be, I guess there's not a hertz or inverse seconds. Yeah, so hertz are the units, or inverse seconds, 1 over seconds. I don't know what other units are used for frequency. And the units of this, because it's 1 over seconds, it'd be inverse time. So 1 over time is the dimension of frequency. What about acceleration? This is denoted by the letter A most of the time, and it's measured in meters per second squared, or meters per second per second. It could also be measured in feet per second squared, and you can probably see that the dimension of this would be length over time squared. Okay? So notice when we write down the dimension, we're not committing to a particular system of units. We're just saying what quantities appear whenever this quantity appears. All right, how about force? This is a little bit more complicated one. We'll come back to this more later, but force denoted by the letter F. In the MKS system of units, it is measured in newtons, and a newton, of course, is a kilogram meter per second squared. Other units that it's sometimes measured in is dynes, that is in grams centimeters per second squared. It's a CGS unit of force, and the dimension would be a mass times a length divided by time squared. Okay, so that would be like a newton is a kilogram meter per second squared. That would be the dimensions of force. Okay, what about pressure? We'll do a couple more of these. Pressure, denoted by the letter P. That is, the MKS units is pascals. And another way of writing it is in newtons per square meter. How much force is being applied per square meter. Another unit would be the dyne per square centimeter. Another unit would be the bar. There are lots of different units for pressure. There's torr, there's millimeters of mercury, all different units, but they all have a dimension of mass over length times time squared. You could probably figure this out. Newtons has mass length over time squared, and you have to divide by 2 lengths, so that length cancels this length, and you have another length left over, so it's mass over length time squared. What about charge? Here, let's delve into some electricity and magnetism. Charge, denoted by often the letter Q or little q. The units in MKS are the coulomb. And in other units, sometimes you'll see stat coulombs, or electrostatic units. And the dimension of this, you cannot express charge in terms of mass, length, and time. It's got its own unit, Q. So that's the dimension, charge. Okay. Should we do one more? Let's see. Well, why don't we stop there? We'll just leave it at that. Okay, so here we're showing how to identify the dimensions of various quantities. And where are we going with this? I'll probably have to stop here, but where we're going with this is we want to be able to find a formula for, let's say, the frequency of vibration of a pendulum, and we can figure out how it depends on these quantities if we want the dimensions to work out right. So these are the dimensions of these quantities. So the dimensions of these quantities, by carefully analyzing them, they can be used to find a formula for frequency. Formula for the frequency of, say, a pendulum. And that is what we will come back to next time. So let's stop there.